So we're going to go ahead and start in 2.6, and this is going to cover some review materials as well. So, we're just going to dive in. So we're going to solve compound inequalities. And when we solve regular inequalities, it's a lot like solving an equation. So we're going to get some of those same review problems in here. And compound inequalities just means that we have more than one statement. So we have two statements. And that's what we mean by a compound inequality. So, and we do this all the time. Like maybe you want to make, that's not a good example. Maybe you want a house that costs more than, I don't know, $200,000, but you want to make sure it doesn't cost, or you want to make sure it costs less than $300,000. So what you're doing is you're making two statements. The price of my house is going to be greater than $2,000, but my house is also going to be, so it'd be, I guess not but, and my house is going to be less than $300,000. So something like that. That's an example of a compound inequality. Okay, so compound inequalities are joined with either and or. An and statement means both have to be true. So your two statements both have to be true. So maybe you're single and you're dating and you're like, I want to find somebody that's, handsome and rich. So you have two qualifications, right? Two things going on. So it narrows the field, right? You find somebody that's both handsome and rich. But an or statement, they don't both have to be. One has to be true. One has to be true. Both can be true in an or statement, but they don't both have to be true, okay? So then you say, well, I'm going to date a guy that's rich or handsome, and then you have more options probably. Okay, so maybe that's not the best example. Okay, so we'll go to some and statements first, and we'll look at those. It says solve the compound inequality. We're going to graph the solution, and we're going to write the solution in interval notation. So it gives us a chance to review those things as well. So we're going to take our first statement, 4x minus 7, I'm just going to recopy it, is less than 9. So we want to solve for x, we want to get x by itself, so we're going to add 7 to both sides. And you might write it that way, you might write it a different way, that's up to you. 9 and 7, what, 16? Okay, and then we divide both sides by 4. Now you might remember there's a little situation when we're dividing inequalities, but it's only if we multiply or divide by a negative sign or a negative number. So we're dividing by a positive number, so we don't have to change the inequality. So if you do divide by a negative, if it had been a negative 4x, we would have divided by negative 4, and then the inequality would have switched the other way. But we're positive, so it's okay. So we get a statement, x is less than 4. Now, I'm going to graph what that looks like here just so you can see it. So when we're talking about graphing here, we're talking about graphing on a number line. There's 0, 1, 2, 3, 4. And so we're saying less than, so that's a lousy parenthesis, but less than 4. All those numbers then, I should have done it in a different color. So we put a parenthesis here to indicate we want all the numbers up to 4, but not including 4. And then we want all the numbers less than 4, okay? So anything that's covered with green, in my little diagram here, that is in the solution set, and for that one statement, okay? But we're going to do a compound inequality, so we have two statements. So now we're going to take the other statement, 5x plus 8 is greater than or equal to 3. So greater than or equal to 3. So we're going to subtract 8. And we get 5x is greater than or equal to negative 5. And so we're going to divide by 5. Now we did not divide by a negative number. So we get x is greater than or equal to, so the inequality is going to stay the same, greater than or equal to negative 1. Now if we were to graph that, it would look like, well, here's 0, here's negative 1. And what you do is you put a square bracket, and then you're talking about all the numbers greater than negative 1. So I know in some textbooks they use what are called the open dot and the closed dot. For graphing on a number line, we use the parenthesis in place of the open dot and the square bracket in place of the closed dot. And this is because it goes right along with the interval notation. So, yeah, just that's a little change you have to pick up on, because I know some textbooks do open dot, closed dot. Okay, so now we want to join these two statements with an and. So we need all the numbers that are less than 4, but they're also, and I keep saying but, and they're also greater than or equal to -1. So what we're talking about is we're talking about this set of numbers right here. So this is going to be a graph of the actual solution. Here's 0, here's -1, 1, 2, 3, 4, and I don't always do elaborate number lines, but you can. And so we're talking about all the numbers that are greater than -1, and they got to be less than 4. So it's not the whole number line, it's just the numbers that are greater than -1 and greater than or equal to -1 and less than 4. That's what the graph looks like. I just don't seem to be able to draw a good parenthesis today. How many solutions are in that set? There's an infinite number of solutions in there. You can't list all the numbers. That's why we graph it, so we can show what the solution looks like. Now, the great thing about graphing these is you can get the interval notation right off of that. So if you're new to interval notation, the way it's written is basically it's going to follow off this graph in this case. So you're going to have a square bracket, -1, and then you put a comma, which says, okay, we're going to start at -1, we're going to include -1, and we're going to go up to 4, but we won't include the 4. So do you see how the graph kind of looks like the interval notation? This is the interval notation. It's called interval notation, and we're going to use it a lot this semester, so you'll want to work on that. I'll try to get some extra review videos in if you have a little trouble, but if you have any problems with this example, you might want to stop the video and rewind it and go over it again just to get some of those basics in that we're talking about here. But we're going to do more examples, so they'll keep coming up and we'll get it. So usually people get the interval notation pretty good, but it takes a while to get used to it. All right. Solve the compound inequality, graph the solution, and write the solution in interval notation. So same type of problem, just the problem is actually a little bit different. Now, you could do this first one a couple ways, but what I'm going to do is I'm going to go ahead and I'm going to distribute the 2. So I get 6x plus 2 is less than or equal to 20. And then I'm going to subtract the 2, and I get 6x is less than or equal to 18. And I'm going to divide by 6. And so I get x is less than or equal to 3. Again, if I were to graph that, it would look like here's 0, here's 3, and square bracket, and this way, less than. Okay? Now we're going to do the other statement. So I'll distribute the 4. 4x minus 4 is less than 2. So let me add 4 to both sides. And I get 4x is less than 6. I'm going to divide both sides by 4. Again, I divided by a positive number. All these cases I'm dividing by a positive, but we'll get to a -1 eventually. But so far, we've just been dividing by positive coefficients on the x term, and so we just can keep the inequality the same way. So x is less than, I do want to reduce that fraction to 3/2. And then if I were to graph that, what we usually do is we say, well, here's 0, here's 1, here's 2. 3/2 is going to be right, if this is 2 and this is 1, 3/2 is going to be in the middle there, so it's like 1.5. And we want x to be less than that. Okay, so this one's going to be a little bit different, isn't it? X is less than 3/2. Okay, now this one is a little bit different. So this time we want to say, okay, x has to be less than or equal to 3. And also, x has to be less than 3/2, or 1.5. So if you were to, let me do this. If you were to put that other number line right underneath, I'll try to make it line up here. Here's 3, here's 1.5 right there, 3/2. Okay, and if you put that right underneath it would look like that. Now you want all the numbers that are in both sets. We could have done this with the other example too, but we want where it overlaps. So we want all of these numbers up to, well, the 3/2, but not including the 3/2, because 3/2 is not in both sets. It's in the top set, but not the bottom one. So that's that yellow area that I highlighted. That's going to be our solution. So I'm going to go over here and graph the solution. So here's 1, 2, 3 didn't click, 2, 1, oops. And then it's going to be right here at 3/2. And I'm going to put that parenthesis right on that 3/2, and I'm going to say it goes this way. Now, how do we write the interval notation? Because this time we're going off toward negative infinity. A lot of times I have students that like to put like a negative infinity here and an infinity here. So they'll remember, okay, if I'm going to the left, I'm going toward negative infinity. If I'm going to the right, I'm going to positive infinity. Now, we always read our intervals, we always read the graph from left to right. So I'm going to start with negative infinity. Oops. And negative infinity always gets a parenthesis. Infinity also always gets a parenthesis because you can't stop at negative infinity, right? If you think of a really small number, I can think of one smaller. So it's more of an idea. We can't really stop there. I'm going to just rewrite it so it looks a little bit neater. Okay, so I'm starting on the left, and I'm following that blue line now. I'm going from negative infinity, comma, to 3/2. And 3/2 is also going to get a parenthesis because I'm not including the 3/2. All right, there we go. That's the interval notation. We'll do more.